VR. $16.9646 minus 13.2629 divided by 15. No, not 15. Where did that come from? Oh, I skipped some steps there. So that is the arctangent of IXL minus IXC over IR. The i's are going to cancel. And so we end up with the arctan of XL minus XC over R. And that's what I was plugging into a moment ago. Which is the arctan, that's really not much better. Arctan of 16.9646 minus 13.2629 divided by 15. What is this in radians?
0.241.
0.241.
If you want more, it's 0, 0.
There's the 0, 0. So, if I know this angle, which I've now marked in green, is pi over 6, I can figure out this angle, which I have which would give me the phase shift of all the currents and VR. It would just be theta minus pi over 6. So, phi for VR, which is the same phi for all of the currents, is 0.241. Try that one again. It's pi over 6 minus 0.2410. I might have said something backwards over here, but it's pi over 6 minus phi 1, which gives me this angle.
0.2826.
Is it 2826?
2826.
28326?
26. Yes.
All right, so I now know this is for the current. I don't know the amplitude yet, so but at least I know that. I know omega, t is a variable. I need to figure out this, I. Well, I can figure I out easily enough. Because the current's the same for everything. I got 4 formulas right here, of which I actually know enough information from one of them. I know the magnitude, I can figure out what the amplitude of the power supply voltage is. I know Z, because we figured it out right there, so I can find the current from the power supply, so I can find the current for everything else. So we need to figure out what is the amplitude of the voltage for the power supply.
7.7688. Oh, was it not 120?
It is, the RMS value is 120. What is the amplitude? What is the relationship between the RMS value and the amplitude?
Is it just 8?
Excuse me?
8 amps?
Oh, for the final answer?
Yeah.
How'd you get that?
Voltage over resistance?
What voltage did you use? 120?
Yeah.
And you need the amplitude. We're looking for amplitudes here. RMS value is an average.
Oh, okay.
A root mean square average.
Then you just do the opposite of root mean square. You can.
No, there's a very, I mean, if you want to derive it from scratch, go for it, but. Who directed this? I feel pretty confident who directed it. A week ago. We even had a witness sitting right there. Who's doing this?
Oh, yeah.
The chemistry guy, Mason. Apparently had a huge impact on their lives. I'm not
Is
gonna
it-
be dreaded.
Delta VP of power supply is equal to the EMF cosine omega t plus phase shift?
That's a generic equation there, there's more direct, all right. So the amplitude is going to be the RMS value times square root of 2.
I don't remember that at all. Yeah.
They're on that board over there, I see, no problem.
Maybe it got lost in all the
It's possible. Yeah, speaking of lost, was working on a game. Still in the preliminary phase, so it's not a huge loss, but cannot find the file where I was doing all my work anywhere. No idea what happened.
We're coding something,
Not at the coding, that's still my new phase.
but it's like a, what kind of game? Computer game?
Role-playing game, you are trying to start a cult.
Is it a computer game?
Yeah. We'll see how far I get before I retire. Before I die.
Like a full 3D image
I-
thing, or
Figured I wasn't going that, no,
like old school?
a lot of text-based pictures.
Ah.
Perhaps video, if I can figure out how long I can play a video without violating copyright. I think it's 6 seconds. I'm not 100% sure. So anyway, RMS value is 120 times the square root of 2. That'll give us our amplitude. That's the 169.7056.
Yes.
So now that I know the amplitude of my power supply, voltage, then the current is going to be 169.7056 volts divided by my impedance, 15.4464. And we end up with
10.9867
units.
amps.
So, the formula for current for my series circuit, this would be for the resistor, for the power supply, for the inductor, for the capacitor, is going to be 10.9867 amps times the cosine of, should give myself more room there, 9.867 amperes times the cosine of omega, which is 376.99 radians per second times time, plus my phase shift for the current, 0.2826. The voltage for the power supply, I know my amplitude now, that is 169.7056 volts times 376.99 radians per second time, plus my phase shift, which I established to be pi over 6, which is
Amplitude of current,
sorry, what?
that's the amplitude of current.
That's the amplitude of current right there, this number right here.
What's the 169.705?
That's the amplitude of the voltage for the power supply.
Should be cosine of 376.9.
Oh, you are, yes. That's a drop trick function among friends. Plus pi over 6, which is 0.52 something. And I don't have a problem leaving it as pi over 6, but probably the other number beneficial at some point. 52359. Now I have to figure out the voltage for the other things. So I know this angle here that's the 0.2826. I just have to figure out amplitudes and phase shifts for VL, VC. Oh, VR. VR, I know what the phase shift is. Cosine of 376.99 radians per second t plus 0.286. So that's, I know VR and IR are in phase. They have to have the same phase shift. How do we find the amplitude here? Well, we have a set of equations. This is the amplitude for the voltage of the resistance. It's going to be equal to the current, big I, which is 10.9867, times the resistance, which is 15. And we get
164.8011.
the amplitude for the capacitor voltage. Well, it's going to be the current, the 10.9867, times the capacitive reactance, which was 13.2629.
145.7161.
I've got 145.
7161.
Volts. Cosine of 376.99 radians per second time plus. What is the phase shift for the voltage phasor for the capacitor?
Negative. Something.
It is something. I'll agree with that. How would you find it?
You would add pi over 2 to. Sorry, minus pi over 2.
Yeah, from that. And what is 0.2826 minus pi over 2?
Negative 1.2882.
All right, and the last one. First we need the amplitude, so IL, which is the same current as everything else because it's series, 10.9867 times XL, which is 16.9646.
$186.2209.
And then the phase shift.
1.8534.
85384.
8534.
8534. All right, so we now have an equation for all the currents and all the voltages. Now let's find out if it works, if we made Carroll's error somewhere. And we're going to do that by figuring out what is the voltage and the current at 0.01 seconds. And the way we do that is we just we have formulas, it's plug and chug. Just make sure you're in radians and not degrees, or you accommodate for that. So, at time equals t equals 0.01 seconds. The current equals the power supply VR VC VL. So it looks like, Paul, we're all counting on you again. Up, and David, up, and also Nate. You got it.
Negative 6 point.
Which one are you doing
I'm
first?
sorry, current.
Okay, negative.
Negative 6.7352.
Thank you.
For voltage of power supply is negative 69.0270.
For the VC, or, yeah, the fourth one,
Oh, yep.
I got 145.14865. 14865.
14865.
Yeah. Is that in volts or?
I hope so, yes.
For VR, it's negative 101.0279.
Volts. Oh, you need to say your units.
Sorry.
He was raised by the wrong pack of wolves.
Yep. And then for voltage of inductor, it's 147.1262.
You said 147?
Yes, 1262. And then some arbitrary unit.
I'll just arbitrarily put a downward carry.
When I did my number, I was in degree, not radians, back then.
Yeah, there was something off there, I wasn't sure where it was.
Sorry, but
Negative 120.2735.
So the whole point is to find the voltage in each component after 0.01 seconds.
All right, so we're doing a quick and dirty check here, or at least a dirty check. If I go from the lower left corner of my box over there to the upper left corner, if I take the left half, I go across the voltage, the power supply, and that's what my voltage is. I go the other direction, I go across those. The question is, do those three add up to that? If they are close enough, then I feel like we've done something right. If they're far off, then yeah, there's an issue.
221.
And it's like 5 off, but
Okay, so you got 64 or 74?
negative 74.
Wait, something.
0.1752373.
I would have expected us to have been closer than that, but there's one thing typed in the wrong spot, and,
Everything is off.
yeah. It should have come out closer, but I
I mean,
feel
we've
like,
also been rounding off some of the digits.
yeah, there's a lot rounding off in there.
Just as a recap, the voltages are the difference in potential across each component.
Yes,
Okay.
And then from a test point taking point of view, you end up with that difference there, and you're going, okay, there's a problem somewhere, how much time do I want to spend? Or do I want to be passive aggressive and make the person who's grading it figure out where your mistake is? Thereby demonstrating passive aggressiveness on my part.
This feels like one of those things that would be like the last question on a test, like to go through this whole process.
Yeah, it would be a long one, but there's a limited amount of time.
So what's that final number you added on?
This
Yeah.
is the sum of the voltages of the components, and it should be the same as the potential across the power supply. The fact that we're off by 5 tells me that it could be a rounding, or it could be I flipped a number somewhere, or someone typed in calculator and flipped a number.
And why do you switch from capital I to lowercase? What's the difference?
In general, the capital letter indicates an amplitude, and the lowercase indicates sort of the instantaneous value, or the formula.
Okay.
So at this time, that's the instantaneous value, or that's the formula for the instantaneous value. Questions to hear before I show you a different way of solving the exact same problem?
Do you have a video of you going through this online too, or something?
I think so.
What is the negative 74 at the very bottom?
I was told that was the sum of those 3 numbers.
Oh, added together. Okay.
It's supposed to equal the instantaneous value of the voltage of the power supply. Or maybe it represents a loss in potential that comes from heating up the wires.
Is that 1752373?
1752373, yes.
Okay.
Obviously, we are not caring about significant figures here. Any questions before I need to erase stuff?